Okay, so we will talk about action potentials, remembering that the last lecture we talked about graded potentials, and we're going to be using a lot of the words that we went over in that lecture. So if you haven't listened to that lecture in a while, I highly recommend you go back, listen to the graded potentials lecture again, and then try to immediately listen to this lecture, because there's a lot of information from the graded potential lecture that you'll use in the action potential lecture. And as usual, I can never get my first slide to advance. There we go. Alright, so what is an action potential? An action potential is a large alteration in the membrane, an electrical alteration. We talked about resting membrane potential, separating opposite charges. When we see a very large alteration in the movements of those different charges, we can get an action potential. Very small alterations, graded potentials. Very large alterations are action potentials. They are very, very rapid, 1 to 4 milliseconds. Remembering again, this is the signal that we talked about when we talked about muscle contraction. We said there's a very short signal from the nervous system that triggers the muscle to contract for 100 times longer. This is that signal, an action potential, very rapid. You can have several repeating hundreds per second. Cells that are capable of action potentials are nerve cells, muscle cells, some of your endocrine cells, which are hormone-producing cells, immune cells, reproductive cells. They all have a specialized plasma membrane that allows them to produce action potentials. A little more vocabulary. So if it is a specialized plasma membrane that can produce an action potential, we call it an excitable membrane. If we're talking about the ability to generate an action potential, if we say this endocrine cell is excitable, it has excitability, that means it can produce an action potential. And the other thing to keep in mind is that nerves are long, and it is through action potentials that a nerve can send a signal over a very long distance. Graded potentials, remember, are short distances. Action potentials are what the nerve would use that goes from the base of your spine to your big toe. Okay, it's about 1 meter long. It's going to use an action potential to communicate. Voltage-gated ion channels, this is why I suggest you go back and listen to the graded potentials. You look at that diagram where we saw the movement of sodium and potassium. So voltage-gated ion channels are what give these membranes the ability to have an action potential. There are lots and lots and lots of voltage-gated ion channels. We're going to focus on just 2 of them. Sodium, which carries a positive charge, and potassium, which carries a positive charge. These 2 ions, charged ions, are going to mediate most of the action potentials. So if we take a look at each gate, the big thing to notice is that the sodium gate has 3 states of being, and the potassium gate has 2. So let's look at sodium first. Sodium can be closed, it can be open, or it can be inactivated. It has what we call, a ball and chain model, okay, because the gate has what looks like a ball and a chain hanging on it. And what this allows the sodium channel to do is to have this inactivated state. And notice that sodium can open and inactivate very, very rapidly. So it can start moving sodium and stop moving sodium very, very fast. This is going to come into play when we talk about an action potential. On the other hand, when we look at a potassium channel, it is closed or it is open. There is no state of inactivation. And because of that, the sodium gates open and close very slowly. This is a diagram of the 7 steps of an action potential, and you will need to know what is occurring at each of the 7 steps. So what I recommend, listen to this lecture, then go back to this slide, because this slide has no writing on it, and talk yourself through every step. Okay? Step 1, this white line represents resting membrane potential right at negative 70 millivolts. Step 2, this dotted red line represents a point of no return, or what we call a threshold. The cell has to depolarize up to the threshold or else it will not fire. Once it reaches the threshold, we see a quick depolarization. Remember, once the cell's charge goes past 0 and it's more positive on the inside than the outside, we have overshooting. Okay? cell overshoots, it comes back down, which is repolarization, coming more negative than resting membrane potential makes it hyperpolarized, and then it returns to rest. So that's the very kind of vague and general happening of an action potential, and we're going to talk more specifically about what's causing that to happen in each step. So step 1, resting membrane potential is close to the potassium equilibrium potential. Remembering that the potassium equilibrium potential is when potassium flows down its concentration gradient and it is met equally by the force of potassium being repelled back by like charges. Those are those two panels we looked at. Potassium flows down its concentration gradient into a sodium compartment. Sodium carries a positive charge, potassium carries a positive charge, it will start to repel it. So when sodium is met by an equal force that it's being repelled by, you have its equilibrium potential. So that's step 1. You're basically just at resting membrane potential. Step 2, the cell received a small signal and it was able to reach its threshold. It depolarized slightly, it reached its threshold. What happened was you had a few sodium gates open through a graded potential. Sodium opens its own gate. So let's say you open one sodium channel and one molecule of sodium gets in. Once it gets in, it's going to open another sodium channel. So now you have 2 sodium channels letting in 2. That's going to open up 2 more, now you have 4, and you get into this explosive positive feedback cycle. So sodium rushes into the cell, opens its own channels, and causes a very quick depolarization, which leads us to step 3, the large upstroke of the membrane potential, and the cell starts to become positive on the inside and negative on the inside or outside. What's more positive on the inside than on the outside, sorry. And what's happening is sodium is rushing down its concentration gradient. There was a lot of sodium outside of the cell. Once the gates open, sodium is low on the inside, so sodium is moving down its concentration gradient. Okay, it's almost reaching its equilibrium potential, whereby the potassium on the inside of the cell is going to start to repel the sodium as it rushes in. At step 4, sodium has reached its equilibrium potential. You get the ball and chain swinging in, deactivating the gate. Okay, so now sodium is trapped inside the cell. It was very, very positive because you have a bunch of positive sodium on the inside of the cell, a bunch of positive potassium inside of the cell. So what happens are the potassium channels open up, and that leads us to step 5. Now we are losing positive charge because potassium is flowing out of the cell, and when the cell goes from positive back towards the resting membrane potential, you have repolarization. So number 5 represents repolarization because we are losing potassium out of the cell. Step 6, potassium channels, remember, close very slowly. So potassium, if it could close quickly, we would not lose too much positive charge, but because it closes slowly, we are losing too much positive charge, causing hyperpolarization. In step 7, the potassium channels finally close and we see the resting membrane potential is restored back to negative 70 millivolts. Now, what you have to keep in mind, and let me just flip back to this picture, is that when we started, we had potassium on the outside and sodium on the inside. When we finish, the opposite is true. Potassium is on the outside and sodium is on the inside. So even though step 1 and step 7 are both resting membrane potential, at step 7, the cell is not ready to fire again. It has to reset the ions. And that's what this slide is for, restoring the action potential. Getting back to step 1 means that the potassium that's outside the cell has to come in, the sodium that's inside the cell has to be forced out. So we had all these ions moving back and forth across the membrane, and it seems like we're talking about the whole cell, but actually we're actually talking about a very small amount of movement compared to the total number of ions in the cell. But it is enough movement to actually cause the alteration in the cell membrane and cause the action potential. So this last bullet point 3 here, is talking about getting from step 7 back to step 1. Resting potential is achieved by a loss of potassium. That's going from step 4 to step 5. That repolarization is caused by losing potassium, not sodium. So in order to get from step 7 back to step 1, we have to turn on, this should say Na for sodium, a sodium-potassium ATPase pump. Why? Because the movement during the action potential of each ion was based on its ability to flow down its concentration gradient. So if you wanted to go the opposite way, you have to use ATP. Because remember, if it's using ATP, it's active transport, and we only use active transport when we're forcing ions to move against the concentration gradient, going from an area of low concentration to high concentration. A little bit of familiarity to action potentials. Any local anesthetic, most things ending in cane, Novocaine, xylocaine, things that the dentist gives you before he drills your teeth, their action is to block the voltage-gated sodium channels. If the sodium channels can never open, you can never get from step 1 to step 2. An action potential can never fire, you can never have a depolarization, the signal cannot be sent, therefore sensations such as pain would be blocked because those are communicated through an action potential. Propagating an action potential. Propagation is moving the action potential from one point in the neuron to another point. That's all propagation is. So when an action potential is produced, it causes currents of its own that are going to depolarize the part of the neuron right next door, adjacent to it. And it's going to produce another action potential at the next site, and so on and so on and so on. So this action potential is actually repeating itself down the length of the neuron. That's called action potential propagation. When we look at the propagation, the action potential experienced by each part of the neuron is virtually identical to the initial action potential. That is in contrast to a graded potential, which remember is conducted decrementally, meaning that the initial depolarization is very strong, and as you move away from the site of initiation, the signal becomes weaker. That's a graded potential. Action potentials produce identical signals to the initial one. So as we move down, it doesn't matter if we're right next to the initial signal or we're far away from the initial signal, the action potential looks the same. Action potentials also can only travel in one direction, away from the site of initiation. How fast can an action potential move? That's velocity. Two things determine how quickly action potentials move. The fiber diameter, how big around is the fiber, and the fiber is talking about the axon of the neuron, and myelination, which is insulation. So fiber diameter first. And if the next time you're in an electronics store, a Best Buy, go look at speaker wire. Okay, cheap speaker wire is very, very thin. Expensive speaker wire is very, very thick. It's very, very large around. Large fiber diameter transmits faster signals. It's the same in the wires in the wall, in speaker wire at Best Buy, and in your body. If the larger the fiber diameter is, the faster the action potential propagates or is able to move, and the more accurate the signal becomes. Myelin, as we saw in the last lecture, is insulation. So myelin provides the insulator, preventing the ions from leaking out across the membrane, making for a more accurate signal. So when a neuron has myelination, it has a faster action potential. Some neurons do not have myelination, so they have a slower signal. The other thing to remember about myelin is, remember, it comes in sections. So there are gaps between the myelin called nodes of Ranvier. That's where the action potentials have to occur, where the myelin is interrupted. Why? Because what we're doing is moving ions from the outside of the cell to the inside of the cell. If we had myelin in the way, there could be no gate there, and there could be no exchange between the outside of the cell and the inside of the cell. So let's say this is our point of initiation. We have our sodium gates. You would also have potassium gates here. You get an action potential. It causes currents to travel down across this next section of myelin, and another action potential is fired here. And then it travels down. Oops, where's my arrow going? It would travel down. The next action potential would occur here, and so on and so on and so on. And that's propagating an action potential. Myelin, very, very important. Okay, loss of myelin at one or even several places occurs in a disease like multiple sclerosis, and many, many diseases affect myelin. And what that does is it slows down or blocks the propagation of the impulse, which is the signal that's trying to be sent. What that results in: poor coordination, lack of sensation, sometimes partial paralysis. This is why myelin is important. Even if you think about the wires in the wall, if we were to open up a panel in the wall and we saw a bunch of wires, if they were red, blue, and green, we would touch them, because the ions cannot come from the wire into our body because they have plastic coating on them or insulation. If we open up a panel in the wall and we saw copper wires, we wouldn't touch them because we could be electrocuted. What's electrocution? When the ions move out of that wire into your body. Okay, so that's what myelin does. It's an insulation. It keeps those ions in the wire in the neuron. Synapse. Now that we can move a signal all the way down one neuron, how do we get that signal to the next neuron? Okay, it happens through a synapse. This is the definition of a synapse: an anatomically specialized junction between two neurons, where the electrical activity in one neuron, the presynaptic, or the one that comes before the junction, can influence the second neuron, the postsynaptic. So if we look here, this gap is the synapse. This is the presynaptic neuron. This is the postsynaptic neuron. And you can see in all four of these pictures, none of these neurons are directly touching each other. The activity, what's going on at a synapse, can increase or decrease the likelihood that the next neuron, the postsynaptic neuron, will fire an action potential. And even though we're dealing in action potentials, when neurons communicate with each other through a synapse, it actually goes to a graded potential. So the action potential in the presynaptic neuron will produce a graded potential in the postsynaptic neuron. And two things can occur. It can either be excitatory or inhibitory. Excitatory is going to bring the postsynaptic neuron closer to that threshold. Inhibitory signals are going to drive the second neuron, the postsynaptic neuron, farther from threshold. So I want you to take a minute right now and think about the words that we use: depolarizing, overshooting, repolarizing, hyperpolarizing. Excitatory is going to be one of those four words: depolarize, repolarize, hyperpolarize, or overshoot. Inhibitory is going to be one of those words: depolarize, hyperpolarize, overshoot, or repolarize. I forgot which one I wasn't saying. So take a minute, pause the lecture, think about what excitatory is doing to the neuron and what inhibitory is doing to the neuron. Because when we look at this chart right here, EPSP, excitatory postsynaptic potential, that's all that stands for. IPSP, inhibitory postsynaptic potential. Here's that threshold. An excitatory synapse is depolarizing. It makes the cell less negative, approaching threshold. Inhibitory synapses are hyperpolarizing. They drive the cell farther from threshold. So saying something is excitatory is the same as saying it's depolarizing. Saying something is inhibitory is the same as saying it's hyperpolarizing. There are two types of synapses. we are going to be dealing mostly with chemical synapses, but I do want to bring up electrical synapses. An electrical synapse is the rare condition when the plasma membranes do have direct contact with each other. They are touching each other. They have a specialized junction, a gap junction, which allows the action potential from one neuron to flow directly into the other neuron. It's very rapid. About the only place in the mammal body you will find it is in the heart, cardiac muscle. Some smooth muscle will have it. If you remember all the way back to histology of cardiac muscle, remember one of the features we looked for were intercalated discs? That's the specialized communication in cardiac muscle that allows the action potential to flow from one cell directly to the next. But the majority of the neurons in your body communicate through a chemical synapse, which means that the neurons do not directly touch each other. So if we look at an enlargement of a chemical synapse, we would have the action potential coming down the axon into the terminal end, and we see all these little vesicles hanging out in the terminal presynaptic axon. These little vesicles have neurotransmitters in them. They have a chemical. When the action potential comes down, it causes these little vesicles to dock, and the vesicles will secrete their product into the gap, the synaptic cleft, and then that chemical will be picked up by the postsynaptic cell. The chemical in these little vesicles will either cause this cell to be excited or depolarize, or cause the second cell to hyperpolarize or be inhibited. Okay, and this is the written version of everything we just said. So the action potential travels down to the slight swelling that houses those chemicals, those neurotransmitters. Once the action potential reaches there, the neurotransmitters are released into the space between the neurons where they can be picked up by the second cell. And that's what we'll talk about in the next lecture. We'll talk about individual neurotransmitters.